Welcome, guys. Today we have webinar, and today Dr. Gaurav is presenting. So, Dr. Gaurav is a graduate in mechanical engineering. He obtained his master's and PhD from IIT Roorkee in the field of fluid power and thermo machines. His research field includes fluid machines and fluid power, CFD, and renewable energy, including hydro, solar, wind, and biomass. Dr. Sani is presently working as an assistant professor in mechanical engineering department at HBTU, Kanpur, India. Prior to this, he was associated with the IIT Kanpur as a postdoc fellow and IIEST Sibpur as a assistant professor. So, welcome, Dr. Gaurav. Yes, floor is yours.
Thank you so much, Dr. Krishna. Let me share my screen, and is it visible to you?
Yes, yes.
Okay. First of all, I would thank Dr. Krishna Kumar for inviting me for this free webinar, and that is being organized with the AI Bridge Tech in association with the AB Aqua Sustainable Solutions (SRLs). Let me begin with the outlines of this webinar. So first of all, we will go through this energy scenario and then hydrokinetic energy, then assessment of this hydrokinetic energy research work, which is being carried out at various locations and site selections, how we basically select a particular site for the installation of hydrokinetic energy, and then we will conclude this webinar on this hydrokinetic energy. As everybody basically concerned with the energy, and it play a very significant role in the living standard of the people, and it is basically governed by the and how the people are living. Their standard of the people is basically analyzed based on the per capita energy consumptions. So if we talk about the India's per capita energy consumption, which is about 1,208 kilowatt hour, which is quite low as compared to the global scale, which is about 3,600 kilowatt hour. If we talk about the renewable energy contributions in India, which is about 46.31%, which contributes approximately 220 gigawatt of the total installed capacity of the 475 kilowatt gigawatt. And this is the latest data that we have taken from the Ministry of New and Renewable Energy in India. If we talk about the renewable energy, so there are a lot of sources are available, and lot of potential is available in India in terms of the various energies, that may be wind energy, that may be solar, that may be geothermal or biofuel or hydropower or waste to energy. But all the energy, if we consider, so hydropower is considered to be the most predictable and the prominent source of renewable energy, because this can contribute significantly to the system, and also it can help the people who are living in remote areas that may access to the energy security. And if we think about this hydrokinetic energy, so that may be available in terms of the water streams, that may be that can also be utilized for the power generation. So, uh, Once we think about the hydropower, so the first thing that comes in our mind is that we need to create a dam, and that water, which is basically stored in the structures, that has to be carried out through some conduits to the machine, and then this machine basically drives a generator, and that generator basically gives us the best form of the energy, that is not the electrical energy. So the power equations available over here is, that is rho GQH. Rho is the density of the water, G is the gravitational acceleration, Q is the flow rate, and H is the net head. So again, the power generated, which is basically available to us by multiplication of the efficiency of the system and then the power equation. But if we talk about the hydrokinetic energy, so we need not to create the intricate structures, civil structures. So what we can have is, we can directly deploy our turbines in the flow, and these flow can be utilized to generate the power by utilizing the kinetic head or the kinetic energy of the water. And we can use number of installation strategies. Here we have seen the vertical orientation of the turbine, and this orientation can basically help us to place the generator outside the flow. Here the power equation is half rho a v cube, and v is the velocity, flow velocity of the water, and a is the frontal area. Suppose we have this type of turbine, h is the height of the blade, and d is the diameter of the blade. So directly we can get the frontal area of the turbine, that is h into d, and rho is the again the density of the water. And so here we can see we have also get the power generated, that is Cp, into this particular equation. Cp is the power coefficient or coefficient of performance of the turbine. So that basically depends what kind of turbine we are utilizing for the generation of the kinetic energy. So next we have is, if we compare the conventional and hydrokinetic energy plants, so we can see that in case of conventional hydro, we are basically utilizing the static head of the that may be created naturally or that is artificially available in terms of the dam or something like that. But in case of kinetic energy, we do not to create any structures, so we can directly get the power. So next is, this is a very lengthy project timelines and ecosystem destruction, because we are obstructing the flow, natural flow, and in case of the hydrokinetic, we are not installing any kind of structure across the natural flow of the river or the canal or something like that. So there is relatively, I would say, a minimal environmental impact on the flora and fauna of the system. So this can be considered as, the hydrokinetic system can be considered as the most environmental friendly, and there is no, I would say, the side effect on the installation of the hydrokinetic power plants. So this hydrokinetic energy is basically, if we talk about the theoretical energy, which is similar to the wind energy systems. So that is half rho a v cube, and you can see the velocity play a significant role in case of the power. So this is cubic relationship with the power, and due to high density of the water, as compare, if we compare with the wind, so we can get significant amount of the power even at the low flow velocity of the water. So there may be number of natural water streams, canals, waterways, gravity-driven pipes contains the hydrokinetic energy. So, but as we have the no limit in case of the conventional hydropower, head-based hydropower plants, but in case of the kinetic energy, we have a batch limit. So, batch limit states that we cannot extract more than 59.3% of the power from any theoretical available power of the system. So, the function that comes over here is the Cp. Cp is the power coefficient of the turbine, and A is the turbine area. Again, we have already discussed it, and V is the flow velocity of the water. So bet limits is basically applicable to the various technologies that is available to us. So this is for the Darius rotor. This is for the ideal propeller kind of hydrokinetic turbines. This is the most less efficient turbine is the Savonius turbines. We can get the maximum CP about 0.15. But in case of Darius one, we can go up to zero point 0.4, yeah, or 40% of the efficiency of the total. So here at the x-axis, we have the tip speed ratio, that is the tangential velocity divided by the flow velocity of water. So, if we think about the hydrokinetic energy, so it is not new. It is like, it is our traditional method of extracting the energy by using the pumping of water. So, in case of the old times, so we were using to grind the grains. So we were having the energy in the rivers, and that was consumed in the form of mechanical power for specific purposes like grinding of grains, pumping of water, like that. But in case of empirical periods, conversion of hydrokinetic energy was started to generate electricity locally from locally available natural resources to meet the localized demand of the rural energy. And this is the growth period, or I would say the transition period, in which we can say there are new technology are being utilized to generate to utilize the hydrokinetic energy, and technological innovations along with the scientific research have been carried out, and since last couple of years, and there are in some of the areas, some of the countries, public policies for the same have also been discussed and developed. But in case of modern period, this period will focus on the large scale hydrokinetic technologies for on grid generations applications in the rivers and the seas. So this is, I would say, this is the evolution of the hydrokinetic energy. We have not reached till now to the modern period, but we are in the transition period between the empirical and establishment of the growth period. So, if we talk about the types of hydrokinetic turbines, we have basically two types of turbines. The first is the axial flow, and the second one is the cross flow kind of turbines. So, the axial flow, as you can see by this figure, so there are blades. These blades are basically shape of airfoil shaped blades, and as you can see, the height requirement is basically because we need to create a submerged situation in case of this axial flow, so we need to have a high depth applications for this. Also we have a sophisticated blades that is basically airfoil shaped, and the manufacturing and the maintenance of these are very critical. So this kind of axial flow turbines are basically suitable for the ocean and tidal application, because we not have the debris over there. We not do not have the constraints for the height, and we can have the efficient self-starting kind of system that have the more suitable or stable torque. And in the case of the cross flow turbines, so in case of cross flow we can have the adjustment with the height, but we can increase the diameter based on the requirement. So these are flow independent. We need to have a omnidirectional flow like that. So in case of cross flow we can basically have a directional flow or indirect, mean the flow can be from the any side. And this can be a self start, that can depend on the rotor what we are using. And they have a good debris handling properties, and that they can also be utilized for the shallow depth applications like in rivers, in canals, or in any structure that is basically man-made. And but the problem with this, there are fluctuating torque generations, and they are they are moderate efficient as compared to the axial flow. But by keeping in view the riverine systems, specifically in various states, so it is recommended by the researchers that cross flow turbine is very suitable for the such kind of applications. So, in case of cross flow hydrokinetic turbines, we have two types of rotor. The first one is the Darius one, and another one is the Savonius rotor. So, the Darius one is basically having the airfoil kind of blades, and these blades can be utilized for the generation of lift and drag over the flow, the water. Another is the Savonius rotor. Savonius is a drag-based kind of structure, and that is basically developed by having two kind of S-shaped blades. But the advantage of this Savonius is it is basically having a better self-starting capabilities, but it is, as we have seen also in case of belt limit, it is having the poor performance. The performance or the efficiency of the Savonius one is the very slow. But in case of Darius one, it is efficient. It is having a high RPM rotor, so that can be utilized for the power generation. But the problem with the Darius one is the it is very less initial starting capabilities and of the complex structure. In order to accommodate the both the rotors, or to minimize the drawback associated with the two rotors, what we have come up with, we have a hybrid rotor. So the hybrid rotor is basically the combination of the hybrid Darius one and the Savonius rotor. So in case of Darius, we are basically keeping the Darius one at the outside of this, and the Savonius rotor is inside of it. So this was basically proposed because we were trying to have a self-starting capabilities without reducing the overall performance of the system. So a hybrid kind of concept is basically proposed, and obviously it is having some of the little complex structure, but it is suitable for the large scale, for the rivers, for the canals, for another kind of application. And the most importantly, it can be utilized for the remote locations where we need not to have a another or specific self-starting system that can basically help us to help rotor to get started even at the low flow of water. So if we talk about the assessment of the hydrokinetic energy potential is, So there are a lot of hydrokinetic potential sites. Here we have the large dam. In the large dams, we may have a different transfer schemes. These transfer schemes may be utilized to transfer the water from one locations to the another locations. And there may be there may be water treatment works that can be utilized for the, they may be driven through the gravity driven pipes or through the open channel flow. So that open channel flow may also be utilized for the hydrokinetic energies. And there may be some coil fired power stations. So in case of cooling towers, we are supplying the water. So these cooling towers channels may also be utilized for the hydrokinetic energy generations. And there may be some measuring structures. So the already existing structures may also be utilized for this power generation. There may be some small bridges, there may be chutes, there may be agricultural irrigated areas that is basically having some kind of channels of the water flow. And we may also have the small runoff river power plants. So the downstream side of structure that can also be utilized for the hydrokinetic power plants. So there may be some wastewater treatment works. So there are a lot of potentials for the hydrokinetic energy. So that can also be utilized for the hydrokinetic energy generation. So so why the assessment is basically necessary once we are talking about the hydrokinetic energy? Because as we understood that the power generation is basically have the relation cubic relationship with the velocity. So there is a small if we are not taking velocity as a serious assessment, so there we are losing lot of energy. So the assessment of hydrokinetic is a first and foremost steps to harness the potential of the hydropower. So there is specifically no standard guidelines are available to us till now, but the technology can be decided by understanding the site condition and potential available. So it is very essential step for the hydrokinetic energy generation, because it is directly cubic relationship with the velocity. So next is why we are using. So you can see over here, this is the water and the water interacting with the turbine. So we have to have a proper understanding of the velocity of the water. So suppose we have the turbines over here, and this is the direction of the flow. So this is basically taken from the in-stream power generation company of the. So they are basically working on the hydrokinetic energy. So this is the different types of blades are utilized for the generation of the turbine, and this is the flow direction of the water. So this is the supporting rod that is basically holding up the whole structure of the turbine and generator, like that. So there are different steps for the hydrokinetic energy assessment. First of all, you have to select a site, and based on the selection of the site, you will see what kind of technology may be applicable to this particular site. Then you will select a device. But in case of site, what you have to go is you have to do the bathymetry, you have to measure the flow velocity, you have to also measure the density variations, temperature variations, like that. And in case of after knowing all these parameters, what you will go for, you will go for the selection of turbine technology that is based on it totally on the site characteristics, what kind of velocity, what kind of variation in the discharge, what kind of variation in the density and the temperatures of the water over there, and that is basically governed over there. So next is the wake characteristics. Suppose a particular technology is having a wake characteristics. So wake characteristics means on installation of a particular turbine or at a certain place, what is the effect of that particular installation of the turbine in the downstream side. So that downstream side basically affect, because we are extracting some of the velocity of out of water. So that will at a certain distance. So that distance is known as wake recovery distance. So different technologies have different wake recovery distances, because they have a lot of uh, that depends on the how much power we are extracting from the water. So if we are the power coefficient is more, so means there may be wake characteristic, wake recovery distance may be more, because that is directly related with the velocity reduction. So different technologies having the different wake recovery distances. So based on the wake recovery distances, because we need to install not a single turbine, we need to install number of turbines. So we need to have an array of the turbines. So similar to the wind energy farms, we may create a hydrokinetic energy farms. So based on the wake recovery distances, you need to have a like what is the effect in the inline effect, and then in the transverse direction effect. So that is basically governed by the wake recovery distance. So we are basically having an idea at what locations we need to install the another kind of turbine. Next is our array management. At what is the management of the array that we can affect little to the water flow. So that is the. So in case of bathymetry, we need to have the contours of the streams and reservoir. There may be some leakage, there may be scour stabilization, water quality studies. These are the studies that we have to do. Dam removal, biological and spills, storage and fill the reservoir. They are the number of steps that we have to take during the bathymetry structure. Technology selections, because technology play a crucial role to tap the hydrokinetic energy. So there may be site, there are nearby manufacturing facilities decide the selection of technology, because there may be some complex structure that may be manufactured only at a certain manufacturing facilities. And we need also have to see what are the technology characteristics such as self-starting capabilities, battery efficiency, and simple structure. And also the installation play a significant role to select a particular turbine technology. And last, we have to see the economic parameters to finally select the particular turbine technology for a particular site. So these are the wake recovery distances, because we need to have a array of the turbines. So there are four parameters basically. They are the wake width, wake length, mean velocity profile, and turbulence intensity. So in this case, wake recovery means the distance from rotor plane to the another point downstream where the velocity has already recovered to upstream value, because this is totally gravity driven flow, because the water is basically, which is we are taking the velocity out of it. So that velocity basically regained by the water because of the gravity flow, because we are having a certain slope in the bed of any channel. So wake is typically characterized by the velocity recovery ratio and turbulent intensity recovery ratio. So suppose this is the rotor that we have placed. So it is having a deficit in the velocity. So again, in the downstream side, it is regaining its velocity. In the downstream, it is regaining its velocity. At 90%, you can say the 90% of the velocity is regained by the water due to the gravity flow. So that is basically known as the wake recovery distances. So this is a key factor in determining the stream-wise spacing, how much distance we have to kept between two types, two different turbines. So and wake recovery is primarily driven by the mixing of wake within the surroundings. So a wake recovery distance is typically defined as in the downstream where center line velocity reaches 90% of the inflow velocity. So that is the wake recovery distance. So this is like number of turbines are installed in a transverse directions. So it is basically extracting some of the velocities. So we have to see at what distance it will recover its original velocity. So these are the management of the array. So this is basically crucial to understand the effect that turbine having each other and sounding environment. So this is like so there are certain velocity. U1 is the initial velocity. U3 is the just downstream. U4 is the south side velocity. So that is the mixed zone. That environment impact such as scour and sediment transport can also be assessed, because because of the mixing of the water, there may be mixing of some of the silt, some of the scouring of the bed may also be take place. So this is also we need to manage. So this is the like management. This is the like a rearrangement of the turbines in the hydropower applications. So this is like that we have to put the turbines in that such a scenario that it will regain its velocity, and how much turbines we have to place in the transverse direction as well. Okay. So there are a lot of research activities which is basically being carried out. Uh, so rotor structure modifications and installation parameters and the comparative performance evaluations, and we have the flow structure alterations, and there are some of the project implementations. Okay. So there, as we have proposed in the previous one, so we have a hybrid rotor. In hybrid rotor, we have the airfoil shape of blades, and in between we have the Savonius kind of structure, which is basically placed in the mid of it, and we have the different orientations of the Savonius blades. At which position we have to place the Savonius rotor to get the maximum initial starting torque, so that can help the rotor to start even at low flow of the water. So here are the placement parameters at what, because suppose this is the velocity profile of the water, and in this profile at what locations we have to put our rotor to get the maximum uh, the maximum power generation. So these four clearance ratio is basically investigated. It is like the ratio of upper clearance to the lower clearance. So this is basically covered. So we have received the maximum performance corresponding to 0.55 value of the clearance ratio. So in this case, the clearance ratio is C1 divided by this C1 by C2, and C1 is the lower clearance and C2 is the upper clearance. And the blockage ratio is basically the how much that this, suppose this is the total area of the canal, and in this total area, how much area is basically occupied by the rotor. This is governed by the blockage ratio. H into D is the area of the rotor, and SW into WW is the area of the channel or the canal. So, so if we see the pressure distribution across the Darius and hybrid case, as the hybrid is basically investigated, so you can see this hybrid rotor is basically, you can see get the additional assistance by the Savonius rotor. So the maximum power can be achieved in case of the hybrid rotor. But in case of the simple Darius one, you can achieve the maximum efficiency as compared to the hybrid one, but the rotor may not even start at the low flow velocity of the water. So we need to have a Savonius part in this in the between. So you can also see, you can also visualize how the water is basically interacting with the the turbine blades during the operation of the during the working of the rotor, both Darius one and the hybrid one, at different time of the working of it. So next, you can also visualize how the vortices are basically generated, and you can see the hybrid rotor is basically generating less vortices. It means it is disturbing low as compared to the Darius one in the downstream side. So that's, you can see, you can visualize the intensity of this zone as compared to the intensity over here, because the hybrid rotor is interacting more effectively to the water, and it is affecting like it is producing less mixing to the downstream side water. So that means you can have the less wake recovery distance, which will help us to 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 install number of turbines as compared to the simple Darius one. So another investigation that we have done on the single Savonius one, because Savonius rotor have the less efficiency. So in this case, what we have done is we have tried to have some augmentation techniques that may help us to get the maximum efficiency out of the Savonius rotor itself only. There is no hybrid one. So we have utilized two deflectors that is of the circular shaped, and so this is the distance L1 and this is the diameter D1. L2 is the distance from it, and D2 is that. This theta and L2 are fixed for this, but we have varied the deflector one. So in this case, you can see this is the conventional Darius one without having any kind of deflector system. But in case of the with deflector system, what we are visualizing it. So this Darius this deflector is basically reducing the effect of the incoming water to the returning blade. So that means that will help us to get the maximum torque, because we are reducing the backward side of drag force based on the returning side blades. So next is, you can see this is the conventional turbines, which is about 0.25% of the power coefficient. But in case of having the deflector system, we can achieve up to 0.35 or 36 kind of power coefficient by utilizing this kind of deflector system augmentation. Next is we have, you can see this is the Savoni in a hybrid rotor with the Savonius part within it, and here you can see only we are utilizing this uh, uh, this kind of blades, variable pitch blades, and these variable pitch blades basically help us to reduce the impact of this Savonius part. So what we have done is we have removed this Savonius part, and we have attempted to create the same kind of force system by having the Darius blades having the variable pitch. So this variable pitch can help us to generate the maximum drag force even at the low flow velocity of the water. So we have removed in this case the Darius, the Savonius part, and we have utilized this variable pitch blades to accommodate the water flow at the low flow velocity of water. So this is the schematic of the hybrid rotor and that we have developed at the our lab, and this is the kind of structure that we have utilized for the generation or for the experimental testings. So this were the lab that we have utilized. So in this case, this is our steel structure that we have tested, and in this case, you can check over here is this is the actual lab and the schematic of it. So two pumps were utilized, two axial flow pumps were utilized to maintain the flow, and this was the sump, and here we have the, this is the test section of it, and in this case we have utilized the testing of hybrid rotor. So here you can see this is your channel, and in this channel the turbine is over here, and this is the rotor over here, and this is a steel channel, a concrete channel just to support the steel channel, and here the water flow direction. These are two bearings to have the smooth flow of the shaft, and the direct RPM sensor is there, and this is the torque transducer that has been utilized to generate the torque. And here you can see the load fulcrum is there, and we are also having the max direct RPM over this RPM sensor. So we have tested it, and there is the effect of blockage ratio. So you can see at the initial tip speed ratio, there is not significant effect on the power coefficient. But as we are increasing the blockage ratio, so you can see at the higher TSR values, the power coefficient is basically increased with the increasing of the blockage ratio. So next is the effect of radius ratio. So if we are increasing the participation of the Savonius part within the Darius one in case of hybrid rotor, so here you can see and the 0.66 value of radius ratio leads to the maximum power coefficient as compared to the other consideration of the radius ratio. So this is the site selection, this is the next part of it. So flow velocity, cross-sectional of this canal, river and water streams. These are the major part for the site selections. And distance for the power evacuation, because this is the major effect. We are generating the power, and this power may have to be evacuated at a certain location. So that has to be taken care during the site selection. And demand and supply is there, because we are generating the power, the supply should be there. And the most important part over here is the debris control and its effect, because there may be certain site that may have lot of debris, there may be a drastic effect on the whole overall structure of the system. And also we need to take care of the probability of the natural calamities. Suppose we need to avoid such a locations that may are more prone to the natural calamities such as floods, such as earthquakes, like that. So if we see the monthly average velocity, and this is the month of the year, so you can see at different kind of possible curves. We have this kind of curve, we have this kind of curve, we have, so we need to evaluate different sites. These are the different sites, and different sites have the different kind of curves for the monthly average velocity. So we need to have a site that may maintain a velocity, because based on the velocity we need to select a particular technology. So if we are having no too much variation within the velocity, so that is, I think, the best suitable one for a particular site. And the debris control, because suppose you can see axial flow kind of turbines, so this is basically obstructing with the natural debris which is available. So we need to have a specific structures to avoid the debris that can basically redirect or direct away the debris. So The low deflecting mechanism can also be used to push or divert big debris out of swept area of the turbine. Diffuser may increase the chance of the damage by floating debris. So these kind of things that need to take care before installing the turbines. So here you can see, because of the silting, the whole structure of the generation of the power is basically destructed. Here you can see debris collected across the river bed. So these debris may interact with the hydrokinetic turbines. So this will directly will affect the operation of the hydrokinetic turbines. So we need to also take care such kind of effect on the power generation. So out of it, if we conclude the this is the hydrokinetic energy is the need of the hour, because we have already explored a lot of hydropower potentials, which is basically potential at base. And this hydrokinetic energy is proven technology, because this is not new. We have been using this since centuries. So this is most predictable in nature and is proven in nature. And the major challenges is to precise prediction of resources, because the assessment of the sites is very crucial in case of the to install the turbines at various locations. And the investigations on the system and site parameter is also very important, because we need to have a particular technology. We need to understand the characteristics of the technology. So this is a lot of investigations are needed to investigate the system and site parameters. And one of the major parameters that we think of it, because we need not to install a single turbine at a particular site. We need to have a number of turbines. So we need to understand the wake recovery characteristics that play a major role. And it is also a major factor for the potential estimation. And the use of existing engineering structures, such as there may be old bridge, there may be some measuring structures that can help us to install the turbines. That may also reduce the construction cost. There is no geological or civil contracting risk, and there is no additional land uses. We are already utilizing the existing structures, so that can also be utilized for the power generation. And this is the major impact, is that we are not having a serious impact on the environment, that natural flora and fauna of the system. So this is basically the need of the hour. So we need to work on it. So I would like to thank you, and my sincere thanks to Professor Ashok Dey, IIT Kanpur, Dr. Shamsher, Vice Chancellor SBTU Kanpur, Dr. R.P. Saini, Professor IIT Roorkee, and Dr. Krishna Kumar for organizing such a nice lecture series and inviting me to attend for continued guidance at the this webinar before and during the beginning of this lecture. All the participants or the listeners. So thank you very much. If there's any question, I can answer.
Thank you, Dr. Sani. Question and answer they can put on the chat, and then we can have it in the later stages. So thank you for your
Okay.
nice presentation.
Okay. Thank you so much.